Well, thank you everybody for coming today to hear about our fourth year design project. My name is Connor, and this is my partner Andrej. We're here to talk to you today about vibrational energy harvesting and pipeline leak detection. So just to give a bit of background about the customer here, pipeline leaks, obviously you've all heard about them. They're very environmentally, or they're bad for the environment. And the leaks have actually cost over $8.5 billion in the past 30 years in three forms: lost product, cleanup costs, and reputational damage. Now, these leaks they attempt to prevent these leaks by implementing leak detection sensors throughout the pipeline, but there's one main problem with these sensors is that it's their power source lifetimes. So an average sensor, which is used in detecting pipeline leaks, is a hydrogen sulfide sensor. It's expected to be used in the field for 5 or more years, but the batteries that come along with it only last about 1 year based on consumption rates. Now this poses a problem. Either the pipeline operating companies pay high maintenance costs to actually continuously replace these batteries, or they let the sensor become ineffective, increasing the risk of larger and larger pipeline leaks. So based on this, any supplemental power source which could be used to recharge that that sensor's battery would be very beneficial. So some requirements for any supplemental power source would be: number one, hopefully generate enough power such to replenish what the sensor uses in a day, and number two, actually generate power at the 32 hertz vibration, which is the fluid-induced flow of an oil pipeline. And the secondary requirements would be actually output a signal which could be used to efficiently charge a battery using these sensors, and number two, have a device cost under $300. To satisfy these requirements, our group proposes the use of a triboelectric nanogenerator. It can directly harvest the vibrations of the pipeline and convert them into power, and it does this by utilizing the triboelectric effect. So before we jump into the details of that, I just wanted to describe some current solutions which are on the market, which really aren't ideal for this purpose. Number one is like large-scale power generation methods that you may know of. This may include solar or wind. These power generation methods aren't ideal for the situation, as the sensors only need very low power requirements. In addition, these pipelines are located in very remote locations, potentially underground or underwater. And in addition, if you are putting a solar panel or a wind turbine up, you're utilizing some of that surface land, which could be used for other uses. And the second group, other vibrational energy harvesters, things like electromagnetic or piezoelectric that you probably have heard of. The electromagnetic, based on our research, is actually better for power generation at a higher frequency range, above the 32 hertz. And the piezoelectrics pose some degradation issues over a 5-year time horizon. Based on these issues, as well as some initial research into triboelectric nanogenerators that shows they are optimal at lower frequencies, we believe this is a good solution for the problem.
So the figure on the right, when the slide comes up, it's taking a second because the image is a bit large. The figure on the right shows a standard triboelectric nanogenerator in contact mode. And so typically these devices have 2 acrylic backbones that are separated by 4 springs. And then on one of the backbones you have an aluminum contact plate, and the aluminum serves as the positive triboelectric material as well as a conductor. And on the other plate you have 2 layers. One is PDMS. Other negative triboelectric materials would work, and we'll discuss that in a couple of slides. And on the back of the PDMS is a copper electrode. Now the reason for that is PDMS is a dielectric, and so in device operation, when the PDMS and the aluminum contact, charge is transferred from the aluminum to the PDMS, and then the PDMS induces a charge on the copper electrode on the back, and the electrodes are connected such that as the plates separate, electrons can flow from the copper to the aluminum, and then when the inverse process happens and the plates approach one another and approach contact, charge flows in the opposite direction from the aluminum to the copper, and in this way the device generates alternating current. So our starting point for our design was a triboelectric nanogenerator designed by a group from Georgia Tech in 2013. And they had fabricated a PTFE aluminum triboelectric nanogenerator, which had an output power of 2.5 milliwatts at a frequency of 14 hertz. Now, one of the things that's not super clear in their paper is the exact vibrational amplitude that they achieved this power output at, but generally they were testing below 3 millimeters, which is around the range that we were looking at. And so what they had done to increase the contact area of their triboelectric plates was actually pattern both the surface of the aluminum and the PTFE. And so this was our starting point, but we needed a device that worked at 32 hertz for the vibration amplitude of 0.5 millimeters. And so we started to think about two things. The first was optimizing performance at our pipeline's vibration frequency. And so this would involve tuning the spring constant of the device structure. And then secondly, in general, we wanted to maximize power output. So we mentioned earlier that our sensor would use 0.272 watt hours per day, and that translates to about 11.3 milliwatts that we would need to generate from our triboelectric nano generator. And so how we could optimize device size, triboelectric material choice, and surface modifications to get that 11.3 milliwatts was really the focus of our design. So a lot of these parameters were actually determined empirically. We had ideas on what we wanted to try, but in terms of what was best for device performance, we really needed a solid testing setup. So the video you're about to see shows how we tested the device using an electrodynamic shaker. And essentially, our triboelectric nano generator is affixed to the shaker. The computer, we're allowed to specify the frequency and the vibration amplitude, and the shaker essentially generates vibration at those parameters. And we connected the triboelectric nano generator to a 50 megohm resistor and connected an oscilloscope across that resistor to calculate the output power of our device. So here's the video. Now the sound you hear is actually the contact of the two plates, the PTFE and the aluminum, as well as a little bit of the shaker. And you see on the scope that we're generating about 120 volts, and it's in a steady waveform. So the main thing that we wanted to start investigating first was the relationship between device size and output power. So theoretically, a larger device should have an increased contact area between the plates, which should increase the amount of charge transfer between the plates and hence the output power. But we wanted to confirm that was true, and so we fabricated 3 devices. They're shown on the top right, the size distribution. One is 5 by 5 centimeters, all the way down to 3 by 3. And all 3 of these devices were tested with the same device structure, the same springs, and all 3 are PTFE and aluminum. And so we wanted to just test that initial design that we had seen in literature to see, does the power output scale with device size? And what we realized was, yes, it does. As we expected, output power increased with device size. Now, this was important because it means that we could focus on all the other modifications that we wanted to make, and then in terms of reaching our final power output goal, we could focus on scaling the device as necessary. And so we started to think about what triboelectric materials we could use. Now, the bottom plate was an easy choice. Aluminum's triboelectrically positive, it's conductive, it was used in the previous design, and it's used in lots of other triboelectric nano generators. But for the top plate, we were debating between PTFE, which is triboelectrically negative, it's not conductive. Neither are most triboelectrically negative materials, so we'll need the copper electrode on the back either way. But really we were thinking about whether we should replace PTFE with PDMS. Now on the one hand, PDMS is cheaper, it's easier to micro-pattern, and so it would potentially allow us to increase our contact area. On the other, PTFE is lower on the triboelectric series, so it should in theory get more charge transfer. And this is where we really started focusing on 2 competing effects. It's PTFE being more triboelectric, offering increased charge transfer and hence increased output power, but also PDMS being easier to pattern and therefore potentially making it easier for us to increase its contact area. And so the first thing we wanted to compare was if we have 2 flat devices, one PDMS and one PTFE, on the same device structure, they're the same size, the same springs, which device performs better? Is it feasible for PDMS to replace PTFE? And we were actually surprised by this result. This shows that the PDMS actually outperformed the PTFE on almost the entire frequency range. We think this might have happened for a couple of reasons. The first potentially being that PTFE might have taken longer to warm up. That's why we can see that the 2 curves actually converge at higher frequency. We performed the test from 10 hertz to 45 hertz. The other thing is that PDMS is stickier, and so it might have helped increase the contact area at lower frequencies, and that potentially could have contributed to that difference that you're seeing early that you don't necessarily expect from the theory. But we felt confident moving forwards with the idea that PDMS could replace the PTFE, and we could start investigating how we could surface modify the PDMS. And so in that respect, we had 3 approaches. The first was just a flat structure, as we explained previously. The second was to actually manually scratch an acrylic mold with a scalpel, and then to spin coat the acrylic mold with PDMS. And the third approach was actually something in Dr. Abdelrahman's lab a new technique that didn't require using a clean room, but was allow us to fabricate structured, organized microchannels onto an acrylic mold, and then again spin coat the PDMS on and get a really nice structured surface. The two images on the top show you, one is on the mold, I think the left is on the mold and the right is on the PDMS, as well as the bottom figure shows the intended structures with this approach. And again, all three of these surface modification approaches didn't require the use of the clean room. Of course, the first one is just flat. And so when we compare the output power of these three devices, again, all being the same size and all using the same spring constants, surface structuring increased our output power by almost a factor of 4.2. Now, one thing that I forgot to mention in the previous slide is that the structured device, only half of the device was structured, half of the PDMS contact plate. Now, the reason for that is before we invested resources into structuring the whole contact plate, we wanted to make sure that we actually saw an increase in output power. And so we were really happy to see that our structured device achieved a power output of almost 200 microwatts. And so had we extrapolated this gain across a full structured surface, we expected to see an 8.4 times increase in our output power.
So now if we move over to the mechanical design of the device, to actually get our prototypes to work in the first place, we had to make a few modifications. Number one was limiting the XY movement. To do this, we added alignment posts through each of the four corners, as you can see here in the picture. In our testing setup, there was just a bit too much movement, and before the posts were added, the plate was actually sliding off the device. Obviously, that's not ideal, so the posts were required. And number two, you can't just allow two plates to vibrate on top of each other, as the actual vibration force itself is not enough to create a large enough separation between the plates to actually harvest the potential. So to increase the separation, the springs are required. So as the vibration force pushes up on the bottom plate, the springs are compressed, and then you get contact between the plates, and then as the vibration force pulls down on the bottom plate, the potential energy stored in those springs continues to press up on the top plate, increasing the separation distance. And now, or I guess our design to actually make our device work at 32 hertz, there's a relationship between the mass of this top plate and the actual spring constant that we use in order to achieve a harmonic resonance at 32 hertz. So we tested 4 different spring constants here. And as you can see, right where the dotted line is, the gray line, the spring constant of 0.011 pounds per millimeter, actually yielded a maximum right around this 32 hertz, the 32 hertz vibration. So from here on, we can conclude that this is an optimal spring constant to be used for pipeline vibration energy harvesting. Now, if we look at some of our secondary requirements that we talked about at the beginning, the device cost should be less than $300. Now, this $300 number actually represents the cost of battery replacement over a sensor lifetime. That includes actual battery costs that they're replacing, as well as the labor that would go into that. And through our analysis, we saw that our device is actually much cheaper than this. The cost of the materials that goes into our prototype, it only totals approximately $3.19. They're all very cheap materials, as copper foil, aluminum foil, PDMS, and some springs. So all very cheap. Now, this doesn't represent the actual final cost of a product. You would need a power management circuit and a device enclosure for a commercial product, but we believe overall the final product would still be much cheaper than the cost of their current operation. So in summary, we feel like the triboelectric generator definitely has potential to be used as a supplemental power source to recharge pipeline sensors. We can conclude this because, one, we can meet any power requirement by simply scaling our device, as we showed in our first analysis. Number two, we can further increase our power output by adding surface structures onto the surfaces. And number three, we identified a spring constant which creates harmonic oscillation at the 32 hertz vibration frequency that we were targeting. Now, as far as some next steps that somebody would have to take in order to create a commercial product, number one is actually investigate power management circuits for high impedance sources. As we said, you would need a power management circuit, as the output of our prototype cannot be used to directly charge a battery. You need to rectify the circuit to DC, as our signal is AC. And number two, to continue on with this project, you should examine various surface structures for maximum charge transfer. We only considered a single structure in the linear pyramid. If there is an alternative structure, it may further improve the power. And number three, to continue with this, you should explore alternative mechanical designs to minimize friction. When we added in the mechanical post into our prototype, it added a degree of friction into the device, and this is lost energy, which could be transferred and used to generate power. So to conclude, I'd just like to thank Dr. Abdelrahman, Dr. Doss, and Mr. Certes. You guys were all instrumental throughout this project. Thank you for all your advice, helping us manufacture and helping us testing. I'd also like to thank Jen Kogan and Dr. Backhouse for providing the administration throughout this course and project. And overall, thank you to the nanotechnology engineering faculty for your teaching and advice over the past 5 years.